In this presentation, I want to talk to you about effect size and strength of association. These are two of the most important concepts in statistical analysis and especially in experimental design. The magnitude of the effect that changes in one variable has on changes in another variable is called effect size. If you reflect on this for just a moment, it should occur to you that effect size is what is of most interest to us when we conduct an experiment. We want to know if our explanatory variable is causing a change in our response variable, and we want to know how big that change is. That is, we want to know the magnitude of the effect. So our efforts should not be focused on looking, for example, at a p-value. Our efforts should be focused on looking at the magnitude of effect. Now, the p-value is related to that magnitude of effect, but it is a means to an end, not an end in itself. The end in itself should be descriptively estimating the size of the effect and then determining what size of an effect we can infer to the population, either in a causal fashion, such as when we have randomization, or a population fashion, such as when we have random sampling. Two variables are related because one variable influences a second variable when we have a causal relationship. These are causal effects. For the association of a categorical variable with a quantitative variable, the effect size can be measured as the difference in means or medians among pairs of groups. For example, suppose we're modeling gas mileage from transmission type. So here we have cars with automatic transmissions, cars with manual transmissions. The effect size can be seen as the difference in average gas mileage, 24.4 miles per gallon for the manual transmission and 17.2 miles per gallon for the automatic transmission, resulting in an effect size of 7.2 miles per gallon. That is, this tells us how much of an average increase we will find in gas mileage if we switch from automatic to manual transmission. For the association of two quantitative variables, the effect size is the slope of the regression line. Imagine if we are looking at the displacement or size of the engine and how that will influence gas mileage. The regression line can provide for us an estimate of the size of that effect. The slope of that line, more specifically, tells us how much change there is in the response variable for every unit change in the explanatory variable. This particular slope tells me, if I multiply it by 100 to put it on an easier to interpret scale of measurement, that if I increase displacement by 100 cubic inches, I expect the gas mileage to go down by 4 miles per gallon on average. Whether an effect size is a measure of effect of an explanatory variable on a response variable depends on the type of association among the two variables. That is, we can have two variables that are related, but really you're not talking about an effect of the explanatory variable on a response variable. There may be a third variable that is causing the relationship between our explanatory and response variable. So when we are estimating effect size, it may not actually be an effect we're estimating, but rather simply an association. So how do we know it's an effect? Declaring an effect depends on us knowing that the relationship is a causal relationship, and that depends on the design of the study. With true experimental designs, we can establish a causal relationship so that the term effect size truly means effect and not just a measure of relationship. Strength of association refers to the proportion of variation in the response variable that is related to variation in the explanatory variable. When we look at this slope of this line, that tells us the size of an effect, but what I also would like to know is how close is the relationship among these variables. That is, I want to look at the variation due to the model as a proportion of the total variation. In this case, that proportion is 0.72. So that tells me that 72% of the total variation in gas mileage from the mean can be explained by the displacement or size of the engine. This is called the coefficient of determination, and it is related to the correlation among these two variables. The correlation is negative 0.85, and if we square that, we get the coefficient of determination of 0.72. The strength of association among two variables also indicates the reliability or consistency of the effect that is measured by effect size. So although effect size and strength of association are two different measures, one of those tells us something about the other. When we look at the slope and see that it is negative 0.041, that tells us how much change there is in the response variable as a function of change in the explanatory variable, but we don't know how consistent that change is. This is a change that takes place on average, but as you know, on average may not be representative of individual points. The stronger the strength of association, the more that this effect can be considered as an effect for each of the points rather than simply on average. It's a measure of the consistency of the effect. Strength of association can be measured for both causal and non-causal associations. So to summarize, when we have an association among two variables that may or may not be causal, to determine causality, we have to have a proper experimental design. When we talk about effect size, we may or may not be indicating the effect of an explanatory variable on a response variable. That depends upon whether we've established causality with a good experimental design. Otherwise, effect size isn't really meaning effect, it's just some indication about the relationship among two variables. Strength of association will then tell us something about the consistency of that effect. We need to focus our attention in experimental design on the size of the effect and the strength of association as a way of helping us understand the relationship among our variables and how those match up with our theoretical expectations.